Have you ever wondered why some of the most powerful tractors ever built never really worked the way they were supposed to? Machines with more horsepower than a semi-truck, designs that pushed engineering to the edge, and ideas that, on paper, looked unstoppable. But once they hit the field, things didn't always go as planned. Because in farming, raw power isn't everything. And sometimes, the bigger the machine, the bigger the problem it creates. Today, we're diving into a series of tractors that were built with bold ambition machines designed to redefine what was possible in agriculture. But along the way, they revealed something far more interesting: the gap between engineering intention and real-world performance. Some of these tractors introduced groundbreaking ideas that are still used today. Others became cautionary tales, examples of what happens when design pushes too far, too fast, or in the wrong direction. And as we go through this list, see if you notice the pattern. It's not just about size. It's not just about horsepower. It's about what happens when innovation meets reality. Before we get into the machines themselves, it helps to understand why tractors like these were even built in the first place. Back in the 1970s and 80s, agriculture, especially in places like the United States, was going through a major transformation. Farms were getting larger, fields were expanding, and efficiency became the top priority. Cover more land, in less time, with fewer passes. And that led to one simple idea: if you want more productivity, build bigger machines. Manufacturers entered what many consider an unofficial horsepower race, each company trying to outdo the other not just in strength, but in size, innovation, and capability. On paper, it made perfect sense. A more powerful tractor could pull wider implements, work faster, and theoretically reduce labor and time. But engineering doesn't exist in a vacuum, because once these machines left the drawing board and entered real fields, new variables started to appear, things that couldn't always be solved by adding more power. Soil conditions, transport limitations, fuel consumption, maintenance complexity, operator fatigue. And suddenly, the question wasn't just how big can we build it? It became, how big is too big? That's where these machines come in. Each one represents a moment where engineering ambition pushed forward but reality pushed back. And the results are a lot more complicated than you might expect. One of the earliest examples of this push toward extreme scale came from a machine that, at first glance, looked like the future of farming: the Ford 1156. Built during the height of the horsepower race, this tractor wasn't designed for small operations or tight spaces. It was built with one goal in mind: handle massive fields as efficiently as possible. At the time, farms across North America were expanding rapidly. Larger implements meant fewer passes, and fewer passes meant saving time, fuel, and labor. So engineers leaned into a simple idea: match those massive implements with equally massive machines. That's where the 1156 came in. With its articulated four-wheel design and a high-output engine pushing into the 500 horsepower range, it had the raw capability to pull some of the largest equipment available at the time. On paper, it checked every box: power, traction, and scale. But this is where expectations started to drift away from reality. Because building a tractor this large didn't just increase its capability, it multiplied its challenges. Transporting it between fields wasn't simple. In many cases, it required planning routes carefully or avoiding public roads altogether. Maintenance became more demanding, not just because of the size, but because of the complexity that came with it. And then there was the engine itself. High-output engines delivered impressive performance, but they also brought increased fuel consumption and operational cost. Running a machine like this wasn't just about having power, it was about being able to sustain it economically. So while the Ford 1156 proved that extreme power was possible, it also revealed something just as important. There's a point where adding more size and strength stops improving efficiency and starts working against it. And that raises a bigger question. If more power doesn't always lead to better results, what happens when you push even further? Decades after machines like the Ford 1156, the industry didn't stop pushing forward. If anything, it doubled down. And that brings us to a much more modern example, the Case IH Steiger Quadtrac 620. At first glance, this machine looks like the answer to many of the problems earlier giants faced. Instead of traditional wheels, it uses a 4-track system designed to spread weight more evenly, reduce soil pressure, and improve traction across different field conditions. From an engineering standpoint, it's a smart evolution. More grip, better stability, less slippage under heavy loads. And with an engine pushing close to 700 horsepower, it has more than enough power to handle the largest implements used in modern agriculture. So on paper, this looks like progress done right. But once again, reality adds complexity, because solving one problem often introduces another. The track system, while effective, is significantly more complex than standard wheels. Maintenance isn't just more expensive, it requires more specialized knowledge, more time, and more downtime when something goes wrong. And then there's the scale of the machine itself. Despite improvements in traction and efficiency, its sheer size still creates limitations. Transporting it between fields can be difficult, especially on public roads. In many cases, it's a machine that performs best when it stays exactly where it is on large, open farmland. But farming isn't always that predictable. Different soil conditions, changing weather, and varying field sizes all demand flexibility. And that's where machines like this start to raise an important question. Are we building tractors to handle every situation, or just optimizing them for ideal conditions? Because when a machine becomes this specialized, this powerful, and this complex, you're not just investing in performance, you're committing to everything that comes with it. If earlier machines pushed size and power, this one pushed something else entirely. Design. The versatile Big Roy 1080 wasn't just built to be bigger, it was built to rethink how a tractor should even be laid out. Instead of placing the engine in the front like almost every conventional tractor, engineers moved it to the rear. The idea was straightforward: improve weight distribution, increase traction, and make better use of its massive power. On paper, it was a bold and logical move. With an engine producing around 600 horsepower and a total weight exceeding 30 tons, Big Roy had more than enough force to handle the largest tillage equipment of its time. And with 8 large wheels, it aimed to maximize ground contact and pulling efficiency. But this is where things started to get complicated, because changing one fundamental part of a machine often affects everything else. Moving the engine to the rear created a serious visibility problem for the operator. From the driver's seat, forward visibility was limited, making it harder to navigate fields, avoid obstacles, or operate safely in tighter conditions. To solve this, engineers introduced a rear-view camera system. And for its time, that was incredibly advanced. But it also introduced new layers of complexity, electronics, maintenance challenges, and reliability concerns that weren't common in agricultural equipment back then. Then came the issue beneath the machine. With that much weight spread across 8 wheels, traction improved, but so did soil impact. Instead of lightly distributing pressure, the machine could create deep ruts under certain conditions, potentially damaging soil structure and affecting future crop performance. And maneuverability? That became another trade-off. A machine this large, with this configuration, simply wasn't built for agility. Turning radius increased, flexibility decreased, and operating it in anything other than wide-open fields became a challenge. In the end, Big Roy became something rare. Not just a powerful tractor, but a one-of-a-kind experiment. It proved that bold ideas can push engineering forward, but they also have to work in the real world. Because when innovation starts solving one problem while creating several others, you're no longer just designing a better machine. You're testing the limits of what actually works. When it comes to bold engineering decisions, sometimes the biggest risks don't come from size. They come from changing what already works. And that's exactly what happened with the John Deere 8850. At a time when most tractors relied on proven 6-cylinder engines, John Deere took a different path. They introduced a V8 engine, something far more common in trucks than in agricultural equipment. The goal was clear. More cylinders meant more power, smoother delivery, and the ability to handle increasingly demanding workloads on large farms. And on paper, it looked like a natural step forward. With around 370 horsepower, the 8850 was one of the most powerful tractors of its era. Combined with its articulated design and advanced drivetrain, it had the capability to convert that power into serious pulling performance. But once again, the reality wasn't so simple, because this wasn't just a more powerful engine, it was a completely different type of engine for this application, and that introduced problems. Fuel consumption increased significantly. Running a V8 under heavy agricultural loads meant higher operating costs day after day, and in farming, where margins can be tight, that matters more than raw performance. Then came reliability. The added complexity of the V8 made maintenance more difficult and more expensive. Repairs weren't as straightforward as with the simpler, well-understood 6-cylinder engines farmers were used to. And when downtime happens during critical seasons, planting or harvesting, it's not just inconvenient, it's costly. So while the 8850 represented a bold attempt to push performance forward, it also highlighted something many engineers already understand. Not every upgrade is an improvement. Sometimes, refining what already works is more valuable than replacing it with something more powerful but less practical. And in this case, the balance tipped the wrong way. The 8850 didn't fail because it lacked capability. It struggled because that capability came with trade-offs many operators weren't willing to accept. By this point, you might notice a pattern. Some engineers chased power, others experimented with design, but in this case, the focus shifted to something even more fundamental: weight. The Upton HT14350 was built around a simple but powerful idea: if you want more traction, make the machine heavier. Because in theory, more weight pressing down on the ground means better grip, and better grip means more of the engine's power actually gets transferred into pulling force. So instead of redesigning the entire drivetrain or increasing complexity, this machine took a more direct approach. It added mass, a lot of it, constructed using extremely thick steel plates and powered by an engine in the 350 horsepower range. The HT14 was significantly heavier than most tractors in its class. It was designed to dig in, hold its ground, and pull without slipping, especially in tough conditions. And in certain situations, it worked. Traction improved. Wheel slip decreased. Pulling performance was strong. But once again, the trade-offs started to surface. Because weight doesn't just affect traction, it affects everything. Transporting a machine this heavy becomes more difficult. Fuel consumption increases, wear and tear on components rises, and perhaps most importantly, the impact on the soil itself becomes a serious concern. Excessive weight can lead to soil compaction. And unlike many mechanical issues, soil damage doesn't fix itself quickly. Compacted soil can reduce water absorption, limit root growth, and ultimately affect crop yields over time. So while the machine delivered short-term performance gains, it introduced long-term consequences. And that brings us back to a familiar theme. Solving one problem without considering the full system often creates new ones somewhere else. In this case, the pursuit of maximum traction came at the cost of sustainability, and that's a trade-off farmers can't afford to ignore. Not every extreme machine was built to chase innovation. Some were built to survive. The Belarus K700 came from a completely different philosophy, one shaped not by competition in the marketplace, but by the demands of harsh, unforgiving environments. Developed during the Soviet era, this tractor wasn't designed to be refined, comfortable, or even particularly efficient by modern standards. It was designed to work, no matter what. With its articulated four-wheel drive system and a large V8 engine producing around 230 horsepower, the K700 had the strength to handle heavy-duty tasks across massive agricultural regions. From frozen ground to dry, compacted soil, It was built to operate where many machines simply couldn't, and in that sense, it succeeded. But that success came with a very different set of trade-offs. Because while Western manufacturers were starting to consider operator comfort, fuel efficiency, and ease of maintenance, the K700 focused almost entirely on durability and raw functionality. The result? A machine that could handle extreme conditions, but offered very little in terms of user experience. The cabin was basic, noise levels were high, vibration during operation was significant. Long hours behind the wheel weren't just tiring, they could be physically demanding. And yet, for its intended environment, those compromises were acceptable. Because when your priority is keeping production running under difficult conditions, comfort becomes secondary. Still, when viewed through a modern lens, the K700 highlights an important contrast. Power and durability alone don't define a great machine, because a tractor isn't just a tool, it's something someone has to operate, maintain, and rely on every single day. And when those human factors are overlooked, even the toughest machines start to show their limits. By the time we reach machines like this, the challenge is no longer just about power or size. It's about how far technology should go. The class Xerion 5000 Track VC represents a different kind of ambition, not brute force, but advanced engineering. And its most distinctive feature isn't hidden under the hood. It's the cab. Unlike traditional tractors, the Xerion 5000 allows the entire operator cab to rotate up to 180 degrees. That means instead of constantly twisting your body to monitor rear-mounted implements, you can simply turn the cab and drive in reverse with full visibility. From a design perspective, it's incredibly clever. Better visibility, improved control, reduced operator strain in certain tasks. On paper, it solves a real problem. But once again, the deeper you go, the more questions start to appear. Because adding this level of functionality doesn't come for free. The rotating cab system introduces mechanical complexity. More moving parts, more systems that can fail, and when something goes wrong, repairs aren't simple, they require specialized knowledge and often higher costs. And that changes the equation, because now, the benefit of improved visibility has to be weighed against increased maintenance, potential downtime, and long-term reliability. Then there's the question of necessity. Not every farming operation requires this level of flexibility. For many tasks, traditional setups already work efficiently. So while the feature is impressive, it isn't always essential. And that leads to a familiar pattern we've seen throughout this list. Innovation that solves a problem, but also creates new considerations. The Xerion 5000 isn't a failure. In many ways, it's a showcase of what modern engineering can achieve. But it also highlights a critical point. Just because technology can do something doesn't always mean it should. Because in real-world operations, simplicity and reliability often matter just as much as innovation. Before the most famous giant tractors ever built took the spotlight, there were machines like this laying the groundwork. The Big Bud 450? At the time of its creation, this was one of the largest and most powerful tractors in the world. Built during the peak of the horsepower race, it represented a clear direction the industry was heading toward bigger machines, capable of handling wider implements across vast fields. With an engine producing around 450 horsepower, the Big Bud 450 had the strength to take on serious workloads. For large-scale farming operations, that kind of power meant fewer passes, more coverage, and potentially higher efficiency. From an engineering perspective, it made sense. Scale up the machine, and you scale up productivity. But once again, the reality wasn't that simple. Because as size increases, so do limitations. One of the biggest challenges with machines like the Big Bud 450 was maneuverability. Turning at the end of a field, something that happens constantly during real operations, became slower and less efficient. Navigating tighter areas or irregular field shapes was even more difficult. And those small inefficiencies add up. A few extra seconds per turn might not seem like much. But over hours of operation, across hundreds of passes, it starts to impact overall productivity. Then there's transport. Moving a machine of this scale between locations isn't always straightforward. Road width, bridge limits, and logistical planning all become factors. In some cases, the machine performs best only when it stays in one place, which reduces flexibility. So, while the Big Bud 450 proved that building massive, high-horsepower tractors was entirely possible, it also revealed a critical limitation. Scaling up doesn't just increase capability, it amplifies every weakness. And that realization would directly influence what came next. Because if this was already pushing the limits, what happens when you go even further? Not all extreme tractors came from large manufacturers. Some of the most unusual ideas came directly from the field. And this is one of them. Back in the 1950s, farmers working with the Fordson E27N Major faced a simple problem. The tractor didn't have enough power. With roughly 45 horsepower, it struggled to handle larger implements as farming demands increased. So, instead of waiting for a new model, they tried to solve it themselves. The idea was bold. Take a standard tractor and add a second engine. In theory, it sounds logical. Double the engines, double the power. And in some ways, it worked. The modified machine produced significantly more output than the original design, allowing it to pull heavier equipment than it ever could before. But this is where theory and engineering reality began to separate, because the tractor wasn't designed to handle that kind of load. The frame, drivetrain, and transmission were all built for a single engine. By adding another, the entire system was pushed beyond its intended limits. Stress increased across every component, and that led to problems. Reliability dropped. Wear and tear accelerated. Breakdowns became more frequent. Operating the machine also became far more complicated. Managing two engines at the same time required more attention, more coordination, and more fuel. In fact, fuel consumption effectively doubled, turning operation into a costly process. So, while the machine gained power, it lost balance. And that's what makes this example so interesting. It wasn't the result of corporate engineering or industry competition, it was a hands-on attempt to solve a real problem. And it shows just how far people are willing to go to push equipment beyond its limits. But it also reinforces a key principle. Just because something can be done, doesn't mean the system as a whole can support it. Because in engineering, every part has to work together. And when one element is pushed too far, everything else feels it. If every machine we've looked at so far pushed the limits, this one erased them. The Big Bud 747 isn't just another large tractor, it's widely considered the largest agricultural tractor ever built. Not as a concept, not as a prototype. As a working machine, at over 8 meters long and more than 4 meters tall, its sheer physical presence is hard to comprehend until you see it next to standard equipment. Everything about it was scaled up to match a single purpose: handle the biggest farming tasks imaginable. And at the heart of it all was an engine built to match that ambition. A massive Detroit diesel unit capable of producing close to 900 horsepower. That's not just more than most tractors. That's in a completely different category. With that kind of power, the 747 could pull enormous implements, covering huge areas of land in a fraction of the time smaller machines would require. In the right conditions, it delivered exactly what it was designed to do: maximum output on a massive scale. But once again, reality comes into play. Because when you build something this extreme, every advantage comes with equally extreme demands. Fuel consumption wasn't just high, it was constant. Keeping a machine like this running required a steady supply of fuel on a scale far beyond typical farm operations. Mobility was limited. This wasn't a tractor you moved casually between fields. It was built to stay where it worked. And then there's the question of practicality. Very few farming operations actually require a machine of this size. For most, the combination of cost, logistics, and operational constraints makes something like the 747 unnecessary. So what does that make it? In many ways, it's more than just a tool. It's a statement, a demonstration of what engineering can achieve when constraints are pushed aside and the focus shifts entirely to scale and capability. And that's why it stands at the end of this list. Because the Big Bud 747 doesn't just represent power, It represents the outer edge of what's possible and the moment where possibility and practicality finally separate. Looking back at all of these machines, a clear pattern starts to emerge. Different decades, different engineering approaches, different goals, but the same underlying challenge. Every one of these tractors was built to solve a real problem: more power, more traction, more efficiency, or better performance under difficult conditions. And in many cases, they succeeded. But they also revealed something just as important. Because in the real world, performance isn't defined by a single number, not horsepower, not size, not even innovation. It's defined by balance. Balance between power and efficiency, between complexity and reliability, between capability and practicality. Push too far in one direction and something else starts to break down. And that's what makes these machines so interesting. They're not just examples of engineering ambition. They're lessons that shaped how modern tractors are designed today, where efficiency, precision, and adaptability often matter more than raw scale. So, instead of asking which one was the biggest or the most powerful, a better question might be, which one got closest to the right balance? And which one pushed just a little too far? Let me know what you think. Because depending on how you look at it, every machine on this list was both impressive and flawed in its own way.